to start with an example of this one, page 334 of your textbook. It's an example showing using the converse. Right, if we just go through what the converse says, does someone want to just do that for me? What does the converse of the similarity theorem say?
If the sides of the triangle are in proportion, all of the angles of the two similar triangles will be equal.
Yeah, so they'll be equiangular. So if the corresponding sides of two triangles are in the same proportion, then the two triangles will be equiangular and hence similar. Because remember, in triangles, if you have the one condition, it implies the other. If you have equiangular, it implies corresponding sides in proportion. If you have corresponding sides in proportion, it implies equiangular. And you need both those conditions for the two triangles to be similar. Okay, so if you look at page 334, example 11, it looks like this. All right, you're given a triangle DGH, and you're given 3 lengths of sides of that triangle. And you're given triangle DEF also with 3 lengths. So all of them are there. All right, it's more about how you set out a question like this. So we're going to prove these two triangles are similar to each other using lengths of sides. It's given away that it's sides. So again, you're going to start off in your 2 triangles. So let's start off in the little triangle, in triangle DEF and triangle DHG. All right, so you take the little triangle and let's take the shortest side in the little triangle, which is DE. And we look at the shortest side in the big triangle DHG. And your shortest side is going to be the 6 and 2. All right, so it's going to be DH. And so that would have given us 4/8, which is equal to 1/2. Okay. Then you have to take the next longest side. So we're going to take EF. Again, going back to DEF first. All right. And your next longest side here is GH. And that's going to be 5/10. And you have to write all of this out, even although it seems very basic. Now, with corresponding sides, it's not good enough to only put 2 sides. You need all 3. You need all 3 to be in proportion. So your longest side in DEF is DF over your longest side in the other triangle, which is DG. And that's going to be 6/12. Which equals 1/2. And only now, because all 3 are in the same ratio or in proportion, we can then say, therefore, triangle DEF. And we really should worry about order. So D is obviously your common angle. All right. And DE matched up to DH. So it's going to be DHG. They generally do give them in the right order, but they don't have to. And your reason's going to be corresponding sides in of triangles, if you like, in proportion. Corresponding sides of triangles are in proportion and hence they're similar. Okay. Is that fine? Please, somebody?
Yes, ma'am.
Okay, fairly easy, not particularly difficult. Obviously, it's given away the fact that you've got lengths of sides. It's not the most common way we prove triangles similar. We generally prove them using equiangular, using angles, but it certainly is a way of doing it. All right, so before I go into a harder example, were any of the homework examples a problem, any that I need to do?
Ma'am, may we please just go over E?
Okay, so which one, what does it look like? A, B, C, D, E. It was the circle one.
Ah, yes, ma'am, with the tangents.
Okay, so if you see it here, is it this one? No, it's the second one. That one. Is that
Yes,
it?
ma'am. Yes,
Okay,
ma'am.
right. Okay, so it's on page 335E. Was there a problem with it, Nick?
I don't think so, ma'am. I think there's a problem with me.
Look, let's do it. Okay. All right. So have I got a pen here? Let's just make sure I've got a pen. All right. AB is the diameter of that circle. So straight away, did you fill that in?
Yes, ma'am.
Okay. And did you say there? C2 equals 90. Angle in?
Semicircle.
And semi. Okay. It's right hard to write like this, but anyway.
Luke said there's a problem.
What's the problem?
He
Yeah,
said,
ma'am. I looked at the video for the solution on the Mindborn textbook because this also confused me. And apparently BD is meant to be perpendicular to CD, not equal.
Oh, okay. So let's fix it. So this must be perpendicular.
Yes,
wow.
ma'am.
Will that help?
Yes, ma'am.
Much more.
Because then you have
They not tell you that DC, they only tell you DC is a tangent. They don't tell you this
yeah,
is a tangent.
you can prove it's a tangent, but
Okay, but BD is meant to be perpendicular. So let's fix that up. That must be perpendicular.
Perpendicular.
Yeah, okay. Yeah, there's lots of errors here. So BD is perpendicular. So that'll change everything, won't it? That's a given.
definitely, ma'am.
Because now you have to prove BDC, that little one, so we can make that one red. If it would allow me to change a color here. It's not very cooperative. There we go. Okay, so we can make this a red triangle. Okay, could do with a thicker. Okay, and we've got to prove it similar to BCA. So you've got your 90-degree angles, and then you've got this angle here equals angle A.
Yes, ma'am.
Tan chord theorem. And so then this one must be equal to that one there. Surely?
Yes, ma'am. Thank you.
Third angle of triangle. And then is the rest quite easy? Does anyone want me to do it in full?
yeah,
Yes, please, ma'am.
Okay. All right. So you just fix up the error. You need the error fixed up. Okay. So now you're going to say in triangle BDC and triangle, oopsie, BCA. Okay. So that's the red one. And then it takes too long to change the color here, but it's that other one, ABC. No? BCA. Yeah. All right. First thing, this little triangle, we're going to say angle D equals angle C2 equals 90. It's not really given, but we proved it above. Okay, 2. Angle C1 is equal to angle A, tan chord theorem. And 3, what's left over, it's B2 is going to equal B1, reason third angle of triangle. So therefore, triangle, and let's call it what they called it in the beginning, BDC. BDC is similar to triangle BCA. Angle, angle, angle. All right, just so you know, this would be worth 3 marks, maybe 4 because you had to do the C2 equals 90. All right, but the 3 marks for down here, if you just gave me line 1 and line 2 and the last line, you don't have to put the third angle of a triangle. You would get 3 out of 3. If you gave me line 1, 2, and 3 without the last line, you would get 3 out of 3. If that makes sense. I always put all of it in. So I always put more, but line 1, 2, and this last line would give you 3 out of 3. Line 1, 2, and 3 would give you 3 out of 3. Okay, just so you know. All right, now they say if AB, which is in the second triangle, and AC is equal to 24, calculate the length of, well, how do we find BC?
Python.
Okay, BC is easy. BC squared is going to equal AB squared, which is 25 squared, minus AC squared, which is 24 squared. And what do you land up with BC? And that's theorem. You put there, theorem of Pythag. And then what did you get BC to equal?
I'm just
7 centimeters.
How much?
7 centimeters.
7, thanks. Okay, so that's a nice famous Pythagorean triple, centimeters, okay? And then to find CD. Well, how are we going to find CD? Well, it's obviously going to come from what, never forget what you've proved above. Okay, so if I want to find CD, I want to find, now we're going to use loops because our order was correct. I want to find CD. Well, I need CA. Well, do I have CA on this side? I do. There's CA. Okay, I've got that. All right, what else do I have from this triangle? Well, I have BC. I've just worked it out. And therefore, on the other triangle, to use the same proportion, I would need BA, and I have that. So to answer part 2, from your similar triangles, you can put your unknown, your CD, and we can say CD over AC is equal to, and I go back to this triangle, BC over BA. And the reason is equiangular triangles. Their sides are in proportion because they were equiangular. So CD is going to equal BC, which we know is 7, times by AC, which you know is 24, divided by AB, which you know is 25, and you can work that out. It's too hard for me today. What is the answer? That's a times, eh? What's the answer to this?
$6.72.
Thank you. 6.72. Like that. That you, Luke? Thanks.
Yes, ma'am.
All right. So sorry, there was a mistake, but we know we're going to find them all.
Thank you, ma'am.
Okay, does that make sense?
Yes, ma'am.
Okay, this would be called, easy to routine, fairly routine. Obviously without a mistake in it. Okay, anything else from the homework?
Ma'am, can we please do D?
The one before.
Yeah.
Okay, let me just clear this page. Yeah, and we're going to go there like that to that one. Okay? No, that's the same one. That one. Is that right? Okay, PB is a tangent. So if you just stop for a moment to that circle, what does B1 equal? What does this angle equal?
Angle C, ma'am.
Angle C, okay. Equals angle C, tan chord, theorem. All right. We've also got parallel lines. So what does this line equal? Well, I mean this angle equal, that one there. What does A1 equal?
B2.
B2, okay. So guess what? Isn't this question going to ask us to prove these two triangles similar to each other? And will they be similar? Have we got enough information? Okay, I think they will be. PAB is this one. ABC is that one. So you start in triangle. PAB. And triangle. ABC. We'll see if the order is correct. Your first thing, take PAB. Must come from that triangle first. And the first thing we saw was B1. So B1 equals C. Tan chord theorem. 2. A1, we saw that, comes from that first mentioned triangle. A1 is equal to B2. Alternate angles. And what do you have to put with alternate angles? Your parallel lines. You have to. Okay, and so the third line would be what's left over. So that's your angle P in that triangle. And that's going to equal to angle A2, the angle that's left over. And that would be third angle of triangle. And so therefore we can say, and we label it as it was. So it's PAB. PAB is similar to triangle ABC. Angle, angle, angle. That would get you 3 marks. Now, even if you couldn't prove that, you assume it true. Never forget that you can assume it true. Now, this means PA in part 2. PA over AB must equal AB over BC. Well, if you've got your order right, can we just use loops? Will PA over AB, working from one triangle, equal AB over BC? Is it one line? Will PA over AB, those two sides, be in the same proportion as AB in the same position over BC? And the answer is yes, it will be, because they are equiangular triangles. So if you've proved this true and you can show, and loops are the best way to do it, if you've got your order correct, then you can show that PA over AB, working from one triangle, equals AB over BC. You do not have to swap from triangle to triangle, because remember, it's a law of proportion that those two can be swapped because they're both AB. All right, and then the third one, now we want AP over BP. Okay, so now I need to change my color so that you can see what we're doing. I'll change it to blue. All right, so if we want AP, now in blue, AP over BP. So it's first and second over first and last. Well, what's that going to equal? Well, that's going to equal first and second over first and last. So it's also one line. AP over PB, or BP, same thing, is equal to AB over AC. Okay, I'm allowed to put dittos, you're not. Equiangular triangles. Okay. John, is that fun?
Yes, thank you, ma'am.
Okay, we're going to do a harder one now. What if this question had gone straight to 3? Didn't have all the stuff in the beginning. Didn't tell you which are the two triangles you had to find. It just went straight to prove that that proportion is correct. And they definitely can do that. So if the question went straight to this, what would you have to work out first in order to get that proportion?
Well, the similar triangles.
Yeah. Okay, and can you read them off? I mean, is it possible? Would this left-hand one give you an idea of what the triangle is? Does it hint towards being the triangle PAB? I mean, it's got to have the side AP in it, and it's got to have the side PB and PB, this side in it. is that going to make up a triangle, APB? And does this side make up a triangle, ABC? So does that hint towards that you've got to break it up to that part? So here it's been scaffolded, but it doesn't have to be. You can go straight to the end thing. So that's what we're going to do now. We're going to do an example where it just goes straight to prove that two triangles have sides and proportions, but they don't tell you which two triangles. Okay, does that make some sense?
Yes, ma'am.
Okay, so let's do one. You need to go further on in your textbook. I'll tell you where it is. I just need to find it in my textbook so I know. Okay, it's example 12. So I think this is it here. Yeah, it's example 12, and it's page 337. Okay, so it says there, it's an example where we are looking for the triangles. So you can read it for yourself. Don't look at the solution, please. But it says circles ABC and ABD intersect at A and B. And so at A and B, they share a common chord. All right, then they tell you AC is a tangent. So that's worth remembering that this is a tangent to the smaller circle. All right, so let's just bear something in mind, knowing that that's a tangent. What would A1 equal?
A D.
Okay, so we know that.
B2.
Not B2. A1 would equal D, wouldn't it? Tan chord theorem. There's the chord. There's the tangent. So your windsurf is upside down. So A1 would equal D. Okay. Then they tell you AD is a tangent to the other circle. So what would A2 equal?
Angle C, ma'am.
Angle C. Okay. All right. So that's before we've read anything. We've know quite a lot of information there. All right. So this is what I mean by this. They go straight into prove that those sides are in proportion. So you've got to locate which triangles you're going to use. And how we'll complicate it is sometimes this will be triangle, sometimes this will be line parallel to one side. You'll go back to theorem 1. So we're not there yet. We're on similar triangles at the moment, but we can put both in. All right, but if you look at this, in your thinking, in your analysis of this problem, can you form two triangles out of this? Does this left-hand side give you a triangle that exists and that you know something about it? BC over AC.
Yes, ma'am.
What would it be? ABC.
Yes, ma'am.
ABC. All right, and it's a triangle and I know stuff about it. This side, the right-hand side, does that form a triangle?
Yeah, yes.
ABD. So quite easy enough, but you have to work it out for yourself. How do we make this harder into another problem? Well, these might be they might be swapped around. You might have to fiddle with that proportion first before you can find your triangles. They will get harder. All right. So in order to answer A, we know we've got to prove those two triangles similar to each other. And we've got all the information. In the beginning, when you put down in triangle ABC and triangle ABD, it does not matter about the order here. It only matters once you've proved them similar. Okay, when you're just mentioning where you're working, it doesn't matter about the order. So let's go through the three things. Remember, ABC is mentioned first. So we're going to talk about A1 equals D, and we saw that. Tan chord theorem. Two. Right? Angle C, because it comes from that triangle, equals A2. Tan chord theorem. And your third thing will be what's left over, which is B1. And that's going to equal B2. Third angle of triangle. And so therefore, triangle, and now you can call it whatever you like, because you're in control here. So if we call it ABC, first, third, and middle, then the other one is going to be called DBA. Now we do need to get the order right, because we want to use loops to get our sides. So it's first, third, middle, DBA. So A was equal to D, the two B's were equal to each other, and C was equal to A. Order is crucial. And now you can easily get your loops right to answer the first question. Where's my pen gone there? All right. Now you can say, therefore, BC over AC. So second and third over first and third is going to give you AB over AD. Therefore, BC over AC is going to give you AB or BA over AD. Same thing. Equiangular triangles. So all that they've taken away is the scaffolding. Please shout or please say something if it doesn't make sense. All right, in B, if we just unpack this, we've got AB times AB equals BC times BD. So this is just in our thinking. All right, so we can make that into our ratios. If we just change the color here, we can undo this cross multiplication and it would be AB over BC equals, what are you left with here? BD over AB. So all of that is the same. And again, does that form the first triangle that we chose? And does that form the second triangle that we chose? And it does. So this part, the scribble here, is really what you're thinking. Now we've got those triangles are similar. We've got that triangle ABC is similar to triangle DBA. Don't have to write it again. We've got that. So now AB is a side that they share. So AB over BC. So first and second with second and third would equal DB over AB. So AB over BC would equal DB over AB. Equiangular triangles. And now if you cross multiply, you're going to get that AB squared because they both shared the side. That's a times there. They shared the side AB and you're done. Okay, so obviously a fairly easy one. Two triangles that are quite obvious, but I promise that they'll get more interesting. They will swap things around in these things and you'll have to work backwards and you'll have to analyze. That's why geometry is so great in problem solving. Okay. Tell me you haven't all disappeared, please.
No, ma'am.
Are you all still there? All right. So unless there's anything else from the homework that was a problem. Okay, what I would like you to do for today, they asked for sort of 10 or 15 minutes now, 10 minutes. All right. So it's exercise, the same exercise we were on. So it's exercise 8.5, or where am I writing? Exercise 8.5, and it's page 335. If you could just do F and G for me, please. F and G, gosh. And then in exercise 8.6, page 339. All right. I think we're just going to do A and B, please. And if you use your 10, 13 minutes now, you could certainly get at least 2 of those done quickly. Then tomorrow we're going to do the proof of the theorem. I'll do that in class with you. I'll mark the homework, and I will leave you with a whole lot of these to do in class tomorrow. And we'll do maybe 1 or 2 of the slightly harder ones. Okay, and that's it from me today, if that's okay. Unless there's anything else, can I just ask, because I can't see the group, Chetsa, did you join us? Maxwell?
Yes, ma'am.
Chetsa
Okay.
is here. His mic, I don't think is working.
Okay, Tyron?
Yes, ma'am.
Okay, and Dante? Dante? Okay, so those of you writing Maths Olympiad later, are there a few of you?
Yes, ma'am.
Okay, good luck. Good luck with that.
Thanks,
And
ma'am.
Ma'am,
I'll
I
see you in
forgot, are we
lesson.
allowed a calculator for that?
No calculators in Maths
What?
Olympiad. No.
No.
You've got to take your brains in with you and work them hard. Why do you think I've spent the whole year telling you no calculators? No calculators are
I
allowed.
can't even factorize. No.
No calculators allowed, guys. Okay, let me just get out of this. Yeah, okay. I'm going to stop sharing this. And I need to just go back to the meet. Eh? Yeah, there we go. Chetsa, you take your picture away. That's not fair. My picture's here. Okay, guys, so no calculators at all. Just your brains working overtime. Okay, but to all of you, is it just Dante that's not there? I'll write to him. Okay, so thank you, guys. Good luck with Maths Olympiad, and I'll see you in class tomorrow, lesson 3. And I'm making good progress on your projects. There's some really great projects, lovely ideas. So thank you for that. I've done 15. I've got 8 to go. I'll try and do some more today. Yeah. So thank you, guys. Have a good afternoon, evening, and stay warm.
Thank you, ma'am.
Thank you, ma'am. Sorry, ma'am.
Thank
Could I quickly speak to you about my long item that you gave me about your corrections?
It's going to stop.